Now let's talk about substitutions using the Brown expressions. So why do we need these substitutions? Suppose that you are implementing this lambda calculus with using the Brown expressions. So you use the Brown expressions. Then in order to implement this lambda calculus, you have to implement operational semantics. And the key operation inside this operation semantics is substitution. So in order to implement the lambda calculus using the Brown expressions, you have to define substitutions so that you can implement this operation semantics. So in the case of original lambda calculus, we have this beta reduction. So applied to E prime is beta reduced to E prime for x in the expression E. So this is called a substitution. And we need a similar operation in the Brown expressions. So let's just say this one is converted to the Brown expression lambda m applied to n. Then we have to write something here, and it's going to correspond to this substitution. And if we recall the meaning of the Brown indexes, what we have to do now is we have to locate the bound variable corresponding to this lambda binder. So in this case, you have to find the bound variable x, which corresponds to this lambda binder. And in the case of the Brown expressions, we don't have variables, but instead we have the Brown indexes. So inside this expression m, you have to locate the Brown index 0, which corresponds to this lambda binder. And then you have to replace it with the argument n. So let's introduce this function sigma m, n. What we are trying to do is to find the Brown index 0 inside the expression m, and then replace it with the argument n. So to indicate the Brown index that we are currently looking for, let's write this subscript 0. So to summarize, this function means that find the Brown index 0 in M and substitute and replace it with the argument n. That's the informal interpretation of this function. So let's see an example. The example is lambda 210. So we have this lambda abstraction, and it is applied to the argument lambda 0. So this is actually an identity function. And suppose that the red x here is this one. So we keep these two lambda binders, and we apply beta reduction to this red x. Then these two lambda binders stay the same. And now this is the body of the lambda abstraction. So what we have to do is basically this one. Find the Brown index 0 from the body. So we find the Brown index 0 here, and then substitute lambda 0, the argument. So basically what we are doing is to calculate this function. This is what we are currently up to. Then what is the result? The result is we have found the Brown index 0, and this becomes the argument. And now you have to adjust these two the Brown indexes because this lambda binder is now gone. So 2 corresponds to this lambda binder. Now this is gone, so therefore this 2 becomes 1. And similarly, this 1 corresponds to this lambda binder, but now this lambda binder is gone, so therefore this 1 becomes 0. So this is the result. So what we observe here is that we have to find the Brown index 0 and substitute the argument for this index 0. But at the same time, you have to adjust other indexes by decrementing them by 1. So that's the first observation. Now, let's consider a slightly more complicated example. This time, we have the body of lambda abstraction, and this is the argument. Okay, so this is the red X. So we are applying this lambda abstraction to this argument. So what we have to do is, you have to find the Brown index 0 inside this expression, and then this one is going to be replaced with the argument. That's what we want to do. But now suppose that here we have another lambda abstraction. So remember that what we needed to do is we are going to remove this one, so this is gone. And here we have to find the Brown index 0 and then substitute the argument for this one. But because of the new lambda binder here, inside this lambda expression, you have to find instead the Brown index 1. You have to somehow account for this new lambda binder. Again, what we are doing is we have to find the Brown index 0 from this body of lambda abstraction. So this is now gone. But because of the new lambda binder here, you have to find the Brown index 1 from here, and then substitute the argument for 1. So the result is this disappears, and this 1 now becomes the argument. And this 0 stays the same because so this 1 becomes the argument, and this 0 stays the same because it corresponds to this lambda binder. And now we have to adjust these two indexes by decrementing them by 1. So 3 becomes 2, 2 becomes 1. So the observation here is that the index that we are trying to find depends on the relative position. It depends on lambda binders found inside of the expression. So let's review the function that we wanted to define. So it was sigma 0 mn. What this thing means is that find the Brown index 0 inside M and then substitute n for that. But now suppose that this is lambda expression. Then you have to find the Brown index 0. But inside this expression m, you have to find the Brown index 1 because you have to account for this lambda binder. So this is going to be something like sigma lambda. So this lambda becomes here sigma mn. But now inside expression m, you have to find index 1 instead of 0. So this becomes 1. So this subscript 1 means that try to find index 1 inside expression m. Then what happens if this expression is again another lambda expression? So inside this expression, you have to find the Brown index 1. Then inside this expression m, you have to find the Brown index 2 because of this new lambda binder. So this can be rewritten as lambda sigma 2 m comma n, which means that try to find the index 2 inside expression m. So we can generalize this observation and we can try to define a function sigma I m n. So this thing means try to find index I inside expression m and then substitute n. So we started with the goal of defining this function sigma 0 mn, but we ended up with this generalized form where you try to find index I in expression m and replace it with this argument n. So let's try to define this generalized form of the function, generalized function. So the goal is to define sigma I mn, and the meaning is try to find index I inside expression m, and then this I becomes the argument n. So easy case first. What happens if this is application? You simply propagate. So this one is sigma I m1 and applied to sigma I m2n. So this is the easy case. What happens if this expression m is another lambda expression? Then the interpretation of this subscript is try to find the index I. But inside the expression m, that means that you have to find index I plus 1 because of this new lambda binder. So this is going to be lambda sigma I plus 1 mn. What happens if the expression m is indeed, if the expression m happens to be the index that we are currently looking for? So this thing means try to find the index I and substitute n for that. So we have just found the index I, so we replaced with n. But what if the index j is less than I? Then, as we have seen in this example, the index less than the index that we are currently looking for should be a local bound variable. So this doesn't change. So similarly here, we don't make a change. What happens if this variable, this index j is greater than I? Then you have to adjust it by decrementing by 1. So this case corresponds to these indexes. 3 becomes 2, 2 becomes 1. So we decrement them by 1. So we have this case. So this completes the definition of the substitution function on the Brown expressions. So this is our first attempt. So this equation works fine. Normally it works fine, but if the expression n happens to contain free variables, then this equation fails. But if this expression n is closed, so where this expression n is closed, then this definition works fine.